Hey, it's Nathan, and today I wanted to go ahead and give like a basic intro into the argument structure of transfinite induction proofs. In the intro proofwriting series that I've been working on, or intro math structures, that is basically intro proofwriting series that I've been working on. I talked about induction, and I had this little aside in there where I was like, "Oh, this is a thing that I'm not going to talk about. This is the video for me talking about that thing." And so transfinite induction is this argument structure that generalizes induction. A lot of times you use it in the context of using the axiom of choice, and it just gives you a way of doing induction with bigger things than the naturals, where you would still want to do induction on those things. So, what do I mean by this? Well, the first place to start off is just to go back to regular induction. So with regular induction, you have a base case, which is like your S of 0 statement, or if you're being more general about it, it's your S of K naught statement. And then you also have an induction step. And so this is where you look at the SK statement implying the SK plus 1th statement for every K a natural number. And when you think about that for a little bit too long, you get to the point of wondering, well, why are the naturals important? And the answer is that they're not really that important. It's just that the structure that they have is important. So if we go ahead and look at the natural numbers with their less than or equal to ordering, the naturals with that ordering is a well-ordered set, or is a well order. And it's order isomorphic, or it's essentially the same as an ordinal. So I haven't talked about ordinals in a very long time. The naturals in particular can be thought of as the first infinite ordinal, or the first countably infinite ordinal. An ordinal is just a transitive set, which means that if you are an element of the set, you are also a subset of the set. And it is well ordered under the epsilon relation. And so I guess that's what a set theorist would say. In my brain, I never read the in symbol as an epsilon, even though it's quote unquote a stylized var epsilon. If you look at the Wikipedia page, it says something like that. But in my mind, it's just the in relation. So ordinals, again, are transitive sets. So that means if you are an element of the set, then you are also a subset of the set. And they're well ordered with respect to the in relation, which is that weird var epsilon thing that we use for element of a set. And well ordered just means that every subset has a least element. Well, just to go ahead and check this for an example, if we look at the set containing the empty set, the set of the empty set, and the set containing the empty set and the set of the empty set, which in words is very weird to say, so this is probably where you should focus on the board, just because it's a gross thing to say out loud. This ordinal fits all of the properties of being both transitive and also a well order under the in relation. And in general, usually we would call this particular ordinal 2. Maybe I did 3. No, we would call it 3. Oh gosh, this is why I don't do this type of math. Okay, so I said it's 3. Okay. So we would call it 3. I wrote 2 on the board. I need to fix that. Gross. That's going to be so much editing. That's what we don't like to do. That's what we avoid. We avoid editing like that, but it's okay. We can do this. This is not a problem. So the naturals are just one ordinal, and one particular example of an infinite ordinal. We want to be able to do induction for any given ordinal. And that's what the argument style of transfinite induction covers. So for transfinite induction, it starts similarly to what we had in basic induction, which is that you have a base case. And so this base case, instead of starting at 0 or some k naught, it starts at 0, the ordinal, or some alpha naught, a particular starting ordinal. And then your induction step has this like split argument. So ordinals, you can't count up to all of them, right? So if you just count all of the counting numbers, you're not going to hit the ordinal that is associated with the naturals in finite time. You have to do some like supremum thing in order to get there. Same thing happens with this induction argument. So what we do is that we have a split case. We have a successor case and a limit ordinal case. So a successor case looks exactly like induction did in the basic sense, where you look at one statement and see if it implies its successor statement. And then for the limit case, that looks a lot like strong induction. So when you're looking at a limit or something that you could not get to by counting up to it, you had to do some supremum to get there. What you do is that you would just assume that all of the statements before it were true and see if all of the statements before it were true, being true, imply that this limit statement is true. So I've been talking about ordinals as like the ones that you can count up to and then the ones that you have to like supremum up to. I need to make that rigorous before we do the transfinite induction example so that you know when you pick up an ordinal what case you fall into. So by definition, a successor ordinal is an ordinal that is the successor of another ordinal. And so the successor operation or the incrementing operation for ordinals is just taking an ordinal plus 1, where an ordinal plus 1 is by definition equal to the set that is that ordinal unioned with the set containing the ordinal that you're adding 1 to. This is a very kind of weird thing to think about if you haven't looked at ordinals before, but it's kind of a natural thing because the way you define addition forces transitivity and keeps the in relation a well order. So it's like the natural way to build new ordinals in this counting method. So for example, if we looked at the first countably infinite ordinal omega, and you look at omega plus 1, well, omega plus 1 would just by definition be equal to omega union the set containing omega. And then if we look at our example from the previous board of 3, well, we can look at 4, and well, 4 is just equal to 3 plus 1, and so as an ordinal, that would be equal to 3 union the set containing 3. And so then if you wrote that in terms of empty sets, you would get this gross bracketed mess. But that is what 4 is as an ordinal. So that's what successor ordinals are. And then limit ordinals, I've kind of already mentioned, are the ones that you can't do this successor operation to get to. So in particular, a limit ordinal is defined to be something that is not 0. It's kind of like a boring example because that's where you start counting. And it's also not a successor ordinal. So you didn't get to that ordinal by counting up to it from somewhere else. So the way that we form limit ordinals is by doing these like supremum operations. So for example, omega is a limit ordinal. So omega, again, whenever I say omega, you should be thinking about the natural numbers with an ordering on it. And then, so another example would be omega 1, which is the first uncountable ordinal, which will be important for what comes in this like kind of silly example that illustrates the structure of transfinite induction proofs. So omega 1 is the interval of ordinals from 0 to omega 1 not inclusive. So it's all of the ordinals that are less than omega 1. Another way to think about this is that this is the supremum of all ordinals, such that the ordinals are countable ordinals. And a supremum of ordinals that is of this form can also be written as a union of these ordinals because they have that transitivity to them. If you're looking at unions of ordinals, the unions of ordinals behave sort of like supremums do. And then another way of writing this is that just omega 1 is the set of all countable ordinals. So the set of all countable ordinals is the first uncountable ordinal. And you're not going to get there by adding 1 to anything, because whenever you take something countable and you add an element to that, you're just going to get another countable set. So omega 1 is in fact a limit ordinal. Just to sort of illustrate how the structure of these things go, I want to do a silly proof. And I say it's silly because I'm going to state it, and then immediately I'm going to give you an answer that is an example of this thing being true. But then I want to do a transfinite induction version of the argument that makes the types of sets that satisfy this property very general. So the property is that there exists a subset of the plane such that no 3 points are collinear, or no 3 points fall on the same line, and the set is uncountable. And so proving this is easy. If you know some things about what sets are uncountable on the plane, you can just take a circle of any radius, centered anywhere, and you're done. So I don't want to do it that way. I want to do something that is actually proving something a little bit stronger, where you can take these points to kind of be anywhere in terms of their relation to one another. Another way you can think about this is like forming uncountably many disjoint triangles in the plane, or things like that. So I just want to go through and give that argument in terms of how you would express it in a transfinite induction version of the thing to illustrate what those things look like. And it's helpful to do this with something that you already know is true, because then you don't run into the wall of like, this feels wrong, right? Hopefully, that was the whole thought process behind doing this particular example. I do have other examples of this happening elsewhere on the channel. So when I was studying for my topology qual, I did some live streams, and in one of those I prove the Alexander subbase theorem, which requires a lot more topology background, and this proof requires a little bit of topology itself. But so if you want a harder, more like necessary place where transfinite induction is used, then I will put that in the description below. But anyway, let's go ahead and continue with this kind of silly thing, just to give you an idea of what the structure of these things look like. All right, so just to go back to the proposition one more time before we start the proof. Proposition says that there exists a set A, a subset of R squared, which is just the plane, such that there's no 3 points A, B, and C in A where A, B, and C are all collinear, and A is an uncountable set. So to start this proof, we're going to go ahead and do the axiom of choice thing we need to do in order to use transfinite induction. So we're to go ahead and let fancy L sub A be the set of lines through a point A, and without loss of generality, we're going to go ahead and focus on the origin. So we're just going to look at L0 for right now, and we're going to take that set of lines and we're going to put it in bijection, or we're going to say that they're the same amount of things via some bijective or one-to-one and onto correspondence between this set of lines and some ordinal. And so that ordinal is uncountable, just because think again about a circle about the origin. The number of lines through the origin that are distinct is going to be at uncountable. So it's going to be some uncountable ordinal. And so the transfinite induction that I need to do needs to happen for statements on all countable ordinals, because I just need to show that A is uncountable. If this statement that I've defined here, that there exists some subset of points where there are x sub alpha for alpha less than gamma points in this set, which is a subset of the plane, such that no 3 points in that set are collinear. If that statement were true for one of the uncountable ordinals that is less than theta, then we would be done. So I only need to do this argument for all of the countable ordinals. Because if I do it for all of the countable ordinals, then, well, the first uncountable ordinal was the set of all countable ones, so I would be able to construct enough points that I would get an uncountable set. So in the base case, well, the S0, S1, and S2 statements are all trivial, because S0, there are no points to look at. S1, you just need to pick 1 point, so you pick the origin. S2, you need to have 2 points, so you go ahead and pick the origin, and you pick a point on the first line in your well-ordered version of the set of lines. And then In the third case, which is like the true base case for this, you go ahead and pick the origin, you pick a point on your first line, and then you pick a point on your second line that is not on the first line. So more generally, you could just take some point that is in the complement of the first line, which is also fine. I think that's what I did on the board. But for construction purposes, as we move forward to make sure that these sets behave nicely, and you want to do it in a very deliberate manner, you would pick a point that's on the second line. And so now that we're done with the base case, we can go ahead and look at the induction step, which splits up into the successor and limit cases. So when we go ahead and look at the successor case, we go ahead and just say, let's suppose that you have some alpha and ordinal less than theta, such that alpha is equal to the successor of some beta, where beta is an ordinal, or that just alpha is beta plus 1. Then by induction hypothesis, there exists a set of x gammas where gamma is less than beta, a subset of the plane, where no 3 points are collinear. We go ahead and look at the union of all of the LXYs, where LXY is the line connecting x and y, which lives in the set of x gammas for gamma less than beta. So then the set of all of those lines is going to be countable. And in particular, if I look at the beta-ith line from my well-ordered set of lines to the origin, and I go ahead and remove all of the points that intersect that beta-ith line that are formed by connecting x and y, such that x and y are elements of the set that's guaranteed by the induction hypothesis, then because there were only countably many lines, I'm only going to get countably many points in that intersection, because lines can only intersect at one point in Euclidean geometry. That's where we're living. Then I'm going to be able to form the appropriate set for the ordinal alpha, which was the successor of beta, by just taking the set that I got from my induction hypothesis and unioning on that new point that I found on the beta line that doesn't coincide with any of the other lines that are defined by 2 points. A little bit hard to visualize. If you're following along, and drawing a picture can be very helpful as you go through these things, even though it's hard to draw a picture for this particular thing because there are infinitely many things running around. It's just that they're countably infinitely many, right? And I'm using that the line is a continuum, and you're removing countably many points from the continuum, so like you still have stuff there. Anyway, so now in the limit case, things are essentially the same. So because I only care about countable ordinals, I can look at an ordinal less than omega 1, and just suppose that ordinal less than omega 1 is a limit ordinal, and that the statement holds for all ordinals that are less than the limit ordinal that we're concerned with. We can go ahead and say that the empty set is not the intersection over all of these ordinals less than our limit ordinal of the alpha-ith line minus whatever points intersect it from the beta-ith set of lines formed from pairs of what is guaranteed by the beta-ith statement. That's kind of a mouthful. So let me just explain the notation again. So L, X, Y, beta is going to be the line connecting X and Y, which is within the set of points guaranteed by the S beta statement. Now, because we're looking at countable ordinals, because all of our ordinals that we care about right now are less than omega 1, I know that the set of those lines are all countable, so when I remove a countable set from a continuum, and I do that countably many times, I'm not going to remove all of the continuum. I'm not going to remove all of that line by doing this. Another way we can write this intersection is just by saying that it's the alpha-ith line minus the union over all beta less than alpha, unioned with over all of those xy's that fall in the set guaranteed by the beta-ith statement of those lines connecting the x and y points from that beta statement. Our countable union of countable sets is still countable, and so when you remove that countable set from this continuum or this line, you're going to be left with stuff left over, which is why this is not equal to the empty set. So I can find a point in there to go ahead and give to the alpha-ith ordinal, which in this case happens to be a limit ordinal. So because I've been able to do this for all countable ordinals, ones that are successors and ones that are limits, and also I have a base case, by transfinite induction, I can do this for all countable ordinals, and well, getting a point for every single countable ordinal would give me a uncountable set which has the desired property, which completes the proof. But anyway, yeah, that's basically it for this video. As always, I'm Nathan. This one was chalk. If you enjoyed this video, give it a thumbs up. And if you would like to see me talk about more math things or just how I'm doing in my PhD experience and as a human and all that stuff, you can subscribe to this channel. But otherwise, that's all I got for you today. Again, I'm Nathan. This is Chalk, and I will see you next time.